Hi everyone, thanks for having me today. I'm Jet. Today I'll be sharing about Simkit, a generative and probabilistic model framework for reinforcement learning. So to introduce myself, I'm a computer science undergraduate at the National University of Singapore, and I'm currently the workshops director at NUS Statistics Society, where we deliver data science and machine learning workshops. My personal interest is in the field of reinforcement learning. During my summer 2020 break, I was fortunate to intern at Grad as a machine learning engineer. Over the last 3 months, I worked on Simkit, which can be used for many pricing and decision-making problems in Grab's ride-hailing and deliveries business. In my sharing, I will introduce the various generative and probabilistic models that I implemented using TensorFlow Probability, a Python library built on TensorFlow to combine probabilistic models and deep learning. Let's begin. So why do we need generative and probabilistic models in the first place? Many pricing, optimization, and decision-making problems make use of reinforcement learning, where the agent learns continuously from its interactions from the environment. With every action taken by the agent that interacts with the environment returns a state and a reward. In contrast to supervised learning, where the label is provided for every entry, reinforcement learning makes use of a reward signal to optimize its algorithm. Reinforcement learning is known to be unstable in training due to sample inefficiency and noisy observations and reward functions. Because the data is so noisy, how do we model the uncertainty in the data? So to model this uncertainty, Simkit proposes two types of models that can model the uncertainty in the data. Conditional generative feature models that model the distribution of states, and probabilistic response models that model the distribution of rewards. The conditional generative feature models model the conditional dependencies among different features. So for example, a feature such as time taken before purchase confirmation could be conditionally dependent on another feature such as the age of the customer. The probabilistic models model the distributional reward to facilitate stable training of reinforcement learning agents, as the agent can learn the uncertainty that comes with each response. Let's start off by introducing the conditional generative feature models. For that, we have the Gaussian Mixture Density Network, or GMDN, and the Conditional Generative Adversarial Network, or CGAN. So before I introduce the GMDN, I need to introduce Gaussian Mixture Models, or GMM. The GMM is a weighted sum of multiple normal distributions. A normal distribution is defined by its mean and its variance, which is what you see here. Pi here refers to the weight assigned to each normal distribution. And when you sum all the weighted normal distributions or components together, you get a Gaussian mixture model. So on the left is an example of a Gaussian mixture model of 3 components. As you can see, the probability density is the sum of all the 3 components. So as you saw previously, a Gaussian mixture model is defined by 3 parameters: the weight, the mean, as well as the variance, which is alpha, mu, and sigma over here. So a Gaussian mixture density network is essentially a neural network that predicts the parameters of the Gaussian mixture model. So a useful property of Gaussian mixture models is, if given enough number of components, it can approximate any smooth density. Therefore, the GMDN can be very useful to model noisy data. The second generative model is the conditional generative adversarial network. First, I need to introduce to you the architecture of a generative adversarial network, or GAN. GANs are very popular today for its image generation capabilities. For example, as you might hear, deepfake. If you know some examples of GANs for image generation, you can share with everyone in the chat down below as well. The generative adversarial network is a deep generative model consisting of 2 neural networks: the generative network that generates the candidates, as well as the discriminative networks that evaluates them. And these 2 networks will contest with each other during optimization. So the GAN framework has been popular in recent years for its performance in image generation, and conditioning features during training allows control over the generation process. The conditional GAN is constructed by feeding the data to be conditioned on to both the generator and the discriminator networks. GANs are known to be unstable in training, and therefore a number of improvements are made in Simkit. The Westerstein loss is used for the models, label smoothing is performed, and a diversity penalty is attached to the discriminator model. Aside from conditional generative feature models, Simkit also has probabilistic feature models. For that, we have the Bayesian neural network, Monte Carlo dropout, as well as the deep ensemble. The Bayesian neural network, unlike an ordinary neural network, has weights that are assigned a probability distribution. Bayesian neural networks can be trained via variational inference. Because Bayesian neural networks weights are assigned a probability distribution whose parameters are estimated during training, the Bayesian neural network can be very useful to estimate uncertainty in the data. The second model is the Monte Carlo dropout, or MC dropout. During training and inference, MC dropout performs a few stochastic forward passes through the neural network with dropout applied. So MC dropout has been shown to approximate to Bayesian inference, like in the Bayesian neural networks that you saw just now in the previous slide. So dropout with neural networks allows modeling of uncertainty without sacrificing either computational complexity or test accuracy. The final model is the deep ensemble, which is an ensemble of randomly initialized neural networks. When models are randomly initialized, they tend to explore diverse modes in the function space and maps the loss landscape as a result. So these deep ensembles actually perform better than Bayesian neural networks in practice because variational Bayesian networks, variational Bayesian methods tend to focus only on a single mode. Therefore, the deep ensemble enables the modeling of uncertainty in the data very well as well. Finally, Simkit also has some methods for evaluating the performance of models. Simkit allows the evaluation of performances using quantitative metrics such as the KL and JS divergence, as well as qualitative visualization. The Kullback-Leibler divergence and Jensen-Shannon divergence, known as KL and JS divergence respectively, are implemented empirically. Empirically means that the dataset is separated into histogram bins first, and then the divergence formula is then applied on each bin. For qualitative visualization, a few probability density plots are also implemented in Simkit for visualization of the model performance. So on the left here, the surface plot represents the probability density function of the two-dimensional data. On the right, this violin plot compares the actual data distribution on the left with the fitted model's probability density function on the right. So with this, we can qualitatively visualize the performance of the model. So let me summarize some key takeaways from my sharing of Simkit. Simkit is a general framework for creating generative and probabilistic models, which in my case was used for reinforcement learning applications. I introduced to you the Gaussian mixture density network and conditional GAN for the conditional generative models. And for the probabilistic models, there are the Bayesian neural network, the Monte Carlo dropout, and the deep ensemble. So this internship was my first experience with probabilistic models and Bayesian statistical concepts, and I'm very grateful to my mentors back at Grad who enabled a fulfilling internship experience for me. I hope that I've shared with you the very interesting types of models that can model uncertainty to be used in big data and noisy environments. Thank you very much. My internship report and code are available in the link here. If you'd like to chat more about Simkit or reinforcement learning or anything else, do reach out to me. Thank you.
So one question we got was, in addition to predicting pricing for different services, what other use cases do you see Simkit being used in?
Okay, so in our case, we used it for pricing and reinforcement learning, but actually Simkit is a general framework for generative and probabilistic models, as I've explained just now. And the key benefit of such models, right, is that it is able to model uncertainty in the data. So in almost any real-world application, there's bound to be a lot of noise in the data. So however your model, right, most machine learning models only predicts a single value. So how certain is your model about that point estimate? So probabilistic models allow you to model the uncertainty there. And for example, in optimization, it can then adjust the weights according to how much uncertainty it may have. Generative models, on the other hand, allow you to model these conditional dependencies that may exist between features. So therefore, the models really can be used in any domain that has noisy data.
So Ku asks, can share more on the MC dropout? like setting the probability of dropout, etc.?
So for MC dropout, the probability of the dropout is a hyperparameter. In this case, it really depends on, so the MC dropout, why it works is because of the stochastic forward passes through the neural network. So one limitation of the MC dropout is that it requires many runs through the neural network in order for it to obtain the uncertainty in the data. So if we have a dropout of a higher probability of dropout, we would need more stochastic forward passes through the network, and that would sacrifice computational complexity. So in this case, it really depends on during inference, when let's say if you deploy the model in the real world applications, how much inference time can you afford to do? So that is how you can. That's one way you can tweak the probability of the dropout in the MC dropout model.
So someone asked, as a fresh grad without any working experience, how can we gain experience in the machine learning and data science domain?
Thanks for the question. Actually, I'm currently an undergraduate at the moment, so I'm also learning how to gain more experience in machine learning and data science as well. But my current approach is first and foremost to look out for the problems that people are trying to solve. So look around you, what are companies trying to solve? What are people trying to solve? What matters to them? For example, a few years back, autonomous vehicles were the thing, right? So what kind of algorithms, what kind of models do we need to implement autonomous vehicles? More recently, there is more work on fake news detection, which is quite a troubling issue, which has wide-ranging implications. And recently, the GPT-3 language model was released, which has a lot of potential as well in the types of applications that can be built with it. So look out for all these problems. You can then create personal projects, find out what difficulties people are facing in these domains. Of course, I don't think we are able to solve them, but at least be familiar with the difficulties and know some of the existing methods that try to resolve that problem. So with that, that's how I try to gain experience in machine learning and data science.